All right, happy Friday, everybody. Come on in. We are officially going to get to, I know I've been promising, the greatest unsolved mystery in computer science. That's what we're talking about today. I promise we're going to get there. But to start you off, here is a problem. Read through this problem, maybe talk to those around you, and I will give you a hint. See if you can think about this problem, and remember that problem that I taught y'all on Wednesday called 2SAT, that one we did that weird final creation where we sort of figured out with two variables. I'll tell you that these two problems are secretly related to one another. So take a few minutes, talk to the people around you, see if you can answer this question underneath based on the prompt. Go ahead. I'm going to make a poll everywhere live. Okay, the poll everywhere should be live now. Oh, wait. It might clock otherwise. Oh, right, it's low on battery. Okay. All right, let's chat about this. So, on Wednesday, I rapid fire dragged y'all through this theoretical final creation problem. And I was like, it comes down to some Boolean values. And then you make this graph and you set the edges between the different values, et cetera, et cetera. None of that's really important. But I think it's an interesting approach to solving a problem, which might not feel like a graph problem. But the big takeaway from that final creation problem was that if you set up the graph appropriately, then you find the strongly connected components of that graph, which is a thing I talked to you about also on Wednesday, and which we now hopefully believe we can find strongly connected components in graph linear time. So if we have our sort of final creation graph, and then we run the algorithm to find the strongly connected components, and then we run topological sort on the strongly connected components, if there exists a path as we're ordering through such that we end up in a true state, then we have a solution to the final exam problem. I know it's probably not clear why those things work, and you can go back and go on, watch the lecture or watch YouTube videos to learn more. But what I really want you to take away from this is that we had this problem that might not have seemed like it was like a graph problem. And we reframed it in a way that was sort of more based on Boolean logic. And then we used that Boolean logic in a clever way to represent it as a graph problem. And then once we had it in graph form, we applied some pretty standard graph algorithms, finding strongly connected components, topological sort, and that gave us a solution to that problem in very efficient time, in graph linear time. What I'm going to try and do today is show you that that solution actually can solve a lot of problems as long as you figure out how to represent them in terms of that problem. This, two coloring, is another problem that could be solved by that exact series of solutions. So the final creation problem and this two coloring problem are both problems that can be reduced, which is the key word of the day, reduced to 2SAT, that magical logical representation problem that we can do strongly connected components and topological sort to find a solution. So kind of taking it back to two coloring, the way that this works is the idea is that we want to be able to mark individual vertices as either red or blue such that every edge is either side of the edge is on different colors. The poll everywhere question just sort of asked you to go through and do it manually. So let's see, does there exist a two coloring of the graph on the left-hand side? I see some thumbs up. Yes, I agree. There is a two coloring solution to that one. What about the one on the right-hand side? Does there exist a two? Thumbs down. I agree in that case. Here, I'll show y'all. Whoops. Oh, wait, sorry. Refresh. Oh, it already refreshed. There we go. Here you can see. Okay, so here you can see what are the sort of final solutions to it. The breaking edge on this one is that thing between B and E. Again, you might be like, Casey, why the heck do I care if I can color a graph between blue and green? Well, actually, imagine that blue and green, or blue and red, represent some states. And you want to be able to bounce back and forth between states, right? Blue and red can kind of represent whatever you want it to. And in the final exam situation, what it may be represented in the graph was whether or not a person was going to be satisfied or dissatisfied with the final exam. But this sort of idea of in the final exam, we had the red and green, meaning the smiley face and the frowny face, oh, that student will be satisfied or they won't. Now we've just got colors, red and blue, but we can apply this to mean a lot of different things. And so what we've got here is, yeah, sometimes you can tell if you will have a satisfaction for this, sometimes you won't. So again, why the heck is Casey teaching you all of these problems that don't feel like they have a lot of applications? Well, what we are going to try and do is we are going to try and see if we can find more connections between these and other difficult to solve problems. And we're going to do a little bit of a historical journey through the troubles of computer science researchers. So what I am talking about when I say how these problems relate to one another, that's what we would say is a reduction. And a reduction is just informally, the way I would describe it is like using an algorithm for one thing to solve a different thing. Isn't that convenient when we can do that? And really, like, the more general we can make these algorithms, the more helpful they can be, right? Like, when we were learning about sorting algorithms, remember I said there's comparison sorts and then there's niche sorts, and niche sorts are ones that like only work for a given thing. We didn't care about those. We only cared about the comparison sorts that can sort any type of thing that implements the compare to, right? And then what's happened there is we've sort of like abstractly genericized those sorting algorithms so they can sort a bunch of things. Now we're talking about a bunch of different solutions that can find different problems. Another example of this, right, is, we were talking about, for example, Dijkstra's shortest path. Depending on what your graph represents, Dijkstra's could tell you the shortest time it takes you to drive from one vertex to the other. It could mean the shortest number of, stop layovers on a plane journey. It could mean the shortest amount of electrical wiring that you have to travel. Like, all of those things are different problems. If articulated into a graph and then run on Dijkstra's, we get a solution to our problem back out. So technically, in that way, we've taken all the complexity of those human problems, reduced them down to this graphical representation, and then run something like Dijkstra's. That's one algorithm that's giving us a lot of different answers as long as we manipulate how we represent the problem. That's really just what I'm talking about. Yeah, we already do this all the time. We reduced implementing a hash set to reducing a hash map, for example. You do lots of things. So also, for example, when we were first learning about Dijkstra's, we were talking about how to do shortest path on an unweighted graph, because Dijkstra's requires weights, right? And so, for example, here, maybe we want to run shortest path, but we don't want to use Dijkstra's. We could take some random graph. We just transform the input. So here, for example, we do have weights. And instead, what I did here, this transformation, this is me sort of abstractly reforming this graph in a way that we can run the unweighted shortest path to get something out. So what I'm doing here is I'm actively changing this problem's representation to meet the required input for a different solution. So here I had weights. If I wanted to reduce that in a way that would let me apply a different algorithm, you could see here I just sort of added in nodes so that instead of there being weights on the edges, now it takes 2 jumps to get from S to U. I didn't have to add a node to make 1 jump from U to T. I added in a node to make it 2 jumps from S to T. So these 2 things are equivalent, though they're just slightly different reframings of one another. And then we run the super useful algorithm, unweighted shortest path. We get this solution that tells us the shortest path, and then we kind of undo that translation. And then bam, we've been able to like generically use this helpful algorithm called unweighted shortest path to get things out. So that's what a reduction is. I promised you that 2 coloring is a reduction for 2sat. So here's more examples of, like why you care about 2 coloring. So here's how we would reduce our 2 coloring to use the 2sat solver. So let me get to, here we go. So for example, I know that in 2sat, I have to take in a series of Booleans. So the transformation is I'm going to take in this graph and I'm going to transform it into a series of Boolean representations. So here you can see either A is red or B is red, and A is not red or B is not red. That's a way of logically representing that this edge here, one of these has to be red and one of these has to be blue. So I've just transformed it into a single Boolean expression. Now, I showed you that there's this thing called 2SAT, and 2SAT can run thanks to strongly connected components in the topological sort and can give us some examples of how to color things. And so by doing this translation from the graph to the Booleans and then running our magical 2SAT algorithm, I got out an answer, and then I transformed that output and put it back into graph terminology, and then boom, there I have a solution. Again, it's not super important that you understand exactly why these individual solutions exist. I'm just trying to give you examples of how we kind of abstract problems to be related to solutions that we already know we can use. Why do I care so much about making these connections, these relationships between problems? Welcome to P versus NP. So this is, like I said, this is, people sort of always call it the largest unsolved mystery in computer science. Here's a YouTube video that goes through it. It's real fun and spicy. There's a bunch of things you could go on the internet and read about this. P versus NP is actually probably one of the few problems in computer science that other people have heard of. It's very famous. It's one of the Millennial Prize problems from the Cook Institute, meaning back in the 70s, they decided that this thing I'm going to explain to you is such a hard problem to solve that if any human anywhere solves it, they're just going to give you a big old cash prize and, probably a Turing Award. And frankly, by the end of this lecture, you'll realize that means if you solve P versus NP, you technically rule the world, all that fun stuff. So what is this? Really what this comes down to is this idea of we have problems, we are humans, and now we have this really awesome tool called the computer to help us with our problems. But not every problem can be efficiently solved by a computer. Now, in school terms, we have probably only written code that can run on our singular laptops and run in what feels like almost instantaneous time. But we live in the data revolution. So many industries now are working with not just thousands, but talking about a scale of billions of data points. That's also why we've been so obsessed with algorithm analysis and efficiency, because even though let's say sorting 30 items, whether that runs in linear time or n log n time seems very similar. Imagine sorting 1 billion items. And once we're talking about that, then we will find that all of those different complexity classes that we have been learning about, some of them fall into the category of what we would call efficient runtimes. And so if a problem can be solved in what we would say polynomial time or faster, and polynomial time is when you have n raised to some constant. So n squared, n cubed, n to the fourth, that's the group of polynomial runtimes. And then as you can imagine, n log n constant, those things, those run faster than that. That's all what we would call within the scope of efficiently solvable runtimes, efficiently solvable algorithms. I'm just going to pause. The bottom half of this slide is but Casey, is it really that efficient if it's n to the 10,000 or something like that? No, actually, that would be ridiculous. Computers actually can't run that. But we are talking about classes. And so for the most part, as long as that constant factor isn't absolutely bonkers, n raised to something is still a runtime that exists within the current capacity of computers to actually execute that runtime at scale. And in particular, what I am also going to talk to you today about is something we call the decision problem category. A decision problem is a problem that has a yes or no answer. The knapsack problem that we did for warm-up on Wednesday is a great example. If I give you the collection of items, you can answer yes or no whether they can fit in the knapsack. And if I ask you, is this the maximum value? The answer is yes or no. That's different from, for example, chess problems, play a game of chess. That doesn't really have a yes or no answer to it, right? Here is the actual clock times of how long it takes a computer to run in these complexity classes at different sizes of n. So like I said, when we're looking at an input of 10 items, Does it really matter that much if it's between like a log n runtime and an n factorial runtime? You can see that the computer can still execute them. But as we start to increase the amount of n, you can see that these 2 to the n and n factorial, these are complexity classes that we would call in the exponential groupings. We literally just put an asterisk in here because that means that would take a computer with the average computing power right now more than 10 to the 100 years to finish computing. That is the power of exponential growth. And we consider that to officially just be like not possible because like humans would die before the computer finishes running. So we consider that then not possible. I don't know, maybe that's like a Wall-E situation and somewhere like the computer's just running without us. But for our purposes, we're just going to consider that impossible. So you can see if you just clock things out, right? Like what a difference. Look at this. Running 10 squared items in 2 to the n takes 4 times 10 to the 11 years to finish running. Versus we can run 10 to the 6 items in n squared time in under a minute. This is the power of exponential, right? So I know sometimes it's hard for us to take in orders of magnitude, but this sort of boundary, if you will, here between the complexity classes, this n squared and this 2 to the n, then becomes a huge limiting factor. And when we are trying to use computers to partner with us to solve some of humanity's most complicated problems. So we've encountered a lot of 2 to the n problems. Remember that original recursive problem for Fibonacci? 2 to the n. Remember the original recursive solution for knapsack? 2 to the n. And then we did dynamic programming, we optimized it, and we got it from 2 to the n into linear time. What that means is that at actual scale, that went from unsolvable by computers to solvable by computers. So that's why that's so powerful. So the journey that I'm about to take you on, like I mentioned, is that computer scientists, I mean, really like the art of computer science, we technically consider to have been birthed with Alan Turing back in the sort of World War II era once we first had our electronic computers. But really it was around like the late 60s and the 70s once, you know, like that Cold War money started pouring into universities and computer science programs. And we started to really kind of explore what are the kinds of problems that computers can solve for us. Because we didn't really have computers that could do very much until that time period. Remember, we did a lot of computational advancements just to get, for example, a man on the moon. I do still teach children, and my favorite, you know, game to play with children is to ask them what's more powerful, the computer that took us to the moon or my watch. The answer is my watch. If you didn't know, computational power has grown so exponentially that every single phone in your pocket right now would be faster than the, quote, supercomputers of the 1970s. So they were working with that level of computational power, and they were asking themselves, how powerful are these computers? What problems can these things really solve? And at that time, they then started to create the complexity classes. So the complexity classes we've all been learning about, so on, they originally came out of this time period in the 70s when people were trying to figure out what problems computers can solve. And they created specifically the grouping for P, which stands for polynomial time, which is a math word that really doesn't mean what this refers to, but computer scientists sometimes are terrible at names. And so the P complexity class came first, and it refers to the set of all decision problems, a problem that has a yes or no answer, that has an algorithm that runs in n to the k runtime, where k is some constant. Because we found even in the 70s that those 1970s computers could run those algorithms. For example, like merge sort, you know, invented around that time, runs in n log n. Those computers could handle sorting at scale with merge sort. But that, you know, like once we got into n factorial, the computers just like ran and we had to fail. So researchers were like, okay, well, clearly if something can run in n to the k time, that is efficient. A computer can do it. We're going to call that grouping of problems P, or polynomial. Then there was a bunch of researchers, and they were working on problems for years. Like some of these were working on these problems for decades. And they were problems that felt like a computer should be able to solve the problem. And the reason that they felt like computers should be able to solve the problem is because they were decision problems where there was a yes or no answer, and you could give a solution and very quickly determine whether that solution worked or not. What do I mean by that? So, let's take a puzzle, for example. It might take you a lot of time to like put the pieces of a puzzle together, right? But if a puzzle is done, very quickly can I look at it and see if all the pieces are fit together. The knapsack problem. It was maybe complicated at the beginning, but if I gave you a solution, you could go through pretty quickly and check like, hey, does the sum of all these weights fit in the knapsack? Does the sum of all these values maximize? Yes, I could verify that. Shortest path. If you didn't know Dijkstra's, it would be probably really hard to go through and find all the permutations and guess Dijkstra's. But if I gave you the exact path and said, hey, here's the path, look at the graph, is this the shortest path? Then that felt like you could go and verify the correctness of that. We call that verification like the proof or the certificate, things like that. And so these problems were really stumping researchers because they were like, okay, I don't know if I can use a computer to say, find the solution to a Sudoku puzzle. But if you give me the solution to a Sudoku puzzle, I can look at it and confirm that it fits. And that's really fast and efficient and rather simple to do. It feels like there must be a way to find those solutions. If the solutions are so deterministic, are so algorithmic that I can go through and really efficiently verify whether or not this is a solved puzzle, can I not just find a way to solve a puzzle that is efficient as well? And so that's sort of the open question right now. And so in order to help us continue to understand those researchers, again, created another complexity class, and this is one we haven't met yet. We call it NP. NP stands for non-deterministic polynomial time. Another terrible name. I don't know what that has to do with it, but the definition of NP is the collection of all decision problems where, if given a suggested solution, you can verify that that solution either works or doesn't work in polynomial time. So P is the set of problems that you can solve in polynomial time, like an algorithm can run efficiently in n squared or faster kind of thing, and you can find a solution. NP is if I give you the answer, can you go back and check it in efficient time? So here's some examples, right? Like light spanning trees are a spanning tree of at most weight k. Yeah, if I go by and check that it really connects every vertex, that verifies that that exists, and that's a pretty efficient thing. I could run that in graph linear time. Two coloring, if I gave you the graph, you could look through the graphs and verify that each edge touches a different color, right? And you could do that in graph linear time. In 2SAT, I hope I already showed you, in 2SAT, I can calculate, and if I gave you an example solution, you could go through and you could verify whether that satisfies everybody. So this is now the largest unsolved mystery in computer science. If a problem is in that group of problems called NP, meaning if you give me a solution, I can efficiently verify that solution. Does that also mean you can efficiently find a solution? Because our guts are yeah, well, Sometimes people call this the when I know it, I see it, the NP class. And if something's in a when I know it, I see it, does that mean that I can also find the solution for it? And actually, as it stands right now, no one has proved this. We still do not have deterministic, logical proof as to one way or the other. And if you prove this, like I said, you will win a Millennium Prize. You will probably instantly become one of the most famous people on the planet because this is a huge problem. And I'm going to spend the rest of class telling you what the implications are of if these two things are in the same complexity class. So, let's say we're trying to do this proof. Like we're trying to figure this out. Let's say we want to prove that everything in NP, that everything that can be affirmed can be solved efficiently. Well, what if, and this is how researchers sort of thought through this in the first place, they're like, well, what if I started with like the hardest problem in NP? Because there's some problems that are a little easier, right? Like I said, like if it's a puzzle, I literally just look at it and see if there's any gaps. That's a really simple verification. But maybe like verifying a Dijkstra's or verifying a two-sat's a little more complicated. So maybe let's find the hardest problem in NP and see if we can prove that it can be solved in P time. Also, I've been harping on this idea of reductions. And so if I'm going to start with the hardest problem and see if I can prove that, because if I can prove the hardest thing can run in a P time, then maybe all of them can run in P time. What if the way to solve that problem existed somewhere else? Like somebody already found a solution and all I need to do is reduce my problem in a way that I can use someone else's algorithm. And this is what was happening with researchers in the 70s, is they were all sort of struggling by themselves, trying to figure out if computers could solve the problem that they were working on individually. And then a gentleman named Cook came up with this concept of reductions and was like, hey, if we retranslate things, you can use my solution on your solution. And so there's this flurry of researchers trying to figure out, can I reduce the NP problem I'm working on to any other problem that has a P-style solution? So maybe instead of just like trying to invent my own solution because they were doing that for decades, let me go out there and look at all the algorithms other people have created that can run in polynomial time and see if I can reduce my problem to theirs so that I can borrow their solution. That birthed another class of problems called NP complete. So as researchers went on this journey to see like, hey, okay, instead of just trying to directly solve my problem, I've realized my problem cannot be solved in efficient time by computers. Let's see if I can reduce my problem to one that does have an efficient solution. And as they went on that journey, they found that, okay, there is this collection of problems that are all in the NP class, but we don't have a current existing efficient solution. So they're all in like the Sudoku or the traveling salesman or the like knapsack without the dynamic programming kind of category where like I have a solution, but it's really inefficient, but it would be efficient to verify it. And then they realized those types of problems, a lot of them could be reframed as one another. So an NP complete problem is considered one that has a universal language of encoding such that you can reduce it to every other NP problem. And so they started to look around and they were like, okay, we feel like if we come up with the right reduction, maybe all these hard problems that we're all stuck on that we can't find an efficient solution for, are they all related? That was actually like the original open question. And I will tell you that, yes, somebody did find a solution for this. And that's what I mentioned there, a gentleman named Cook that we started to talk about. Also, this is one of those, like, you know how calculus was kind of like simultaneously discovered by two different people on other sides of the world from one another? This is the same thing. A gentleman named Cook and a gentleman named Levin both came up with this realization simultaneously, but it happened in 1971 in the thick of the Cold War. And guess what? America wasn't talking to the USSR at that time. So now we give them both simultaneous credit, though they were not communicating because they both independently came up with this. They came up with what we call the Cook-Levin theory, which is this single sentence: if a set S of strings is accepted by some non-deterministic Turing machine within polynomial time, then S is P reducible to that particular solution. That is the sentence. There is a 1.5-page mathematical proof on it. I will admit that proof makes no sense to me, but maybe you are a wonderful logical genius and you can go read it. But this sentence won Cook the Turing Award. The Turing Award is the computer science equivalent of the Nobel Prize. That problem was 3-sat. What Cook proved was that collection of extra hard NP problems that can be verified in polynomial time but do not have a polynomial time solution, that all of those, if they can be reduced down, they can be interpreted as 3-sat. So 2-sat, that problem that I taught you, that's where you take in 2 Booleans and determine satisfaction. 3-sat is the exact same problem, but 3 Booleans at a time instead of 2. 3-sat is a problem that if you give me a suggested solution for it, I can verify in polynomial time that that solution exists. But as of now, there is no P polynomial efficient solution for it. So that magic that we did before, where I was like, okay, like you take this problem, you put it into 2-sat format, you find the strongly connected components, you run topological sort, boom, you got an answer, doesn't work for 3-sat. So yes, exactly. Remember when we were first learning this, like originally our first try at 2-sat was 2 to the Q, where Q stood for the number of questions. But then we came up with that really clever graph sort of situation. It reduced down to the graph linear time. Cool. We cannot do the same for 3-sat as it turns out, unfortunately. So though we continue to not have a efficient solution, once Cook published 3-sat as a problem, like I said, all those researchers that were hanging out and they were like, am I just dumb or is my problem really hard? That's really where they were at, right? Once we published this, immediately what happened is those researchers were like, oh, well, if I can reduce my problem to 3-sat, then that means I'm not dumb. I'm just working on an unsolvable problem. And so computer scientists everywhere started figuring out, is the problem that I am currently trying to solve, can it be reduced to 3-sat? And very quickly, we found, what is this? 21, so like really complicated problems that all reduced to 3-sat. So that grouping of the NP complete problems, suddenly all of these are now related, meaning if somebody somewhere finds a solution to 3-sat, well, you've just also simultaneously solved all of these problems because of reductions. Yes. So in 1972, a gentleman named Karp, he got another award and won a bunch of things by just going around and collecting all of these reductions and essentially proving, hey, it's like Cook came up with the problem. Karp went through and said, look at all of these problems are that problem in disguise because of reductions. But wait, there's more. Actually, by 1979, there were at least 300 NP complete problems. And they actually published a physical book. This is the cover of the book. And I will say that when we originally made these slides, I want to say the first time I gave this lecture was like 2019. I just literally went through the Paul Allen building and went through all my colleagues' bookcases. And I found a bunch of them literally had this physical book. Every computer scientist at the time bought this book because they were like, am I dumb or am I trying to solve an impossible problem, right? Like this was your easy out. Like, oh, just kidding. If it reduces to 3 sat, then I can't solve it, right? Add it to the list. So there was 300 problems, took about 100 pages to list them all. And as it turns out, no one's actually bothered to make a comprehensive list of all of these problems since, because there's so many more. Ever since that time, now researchers everywhere, it's standard practice to see, does my problem reduce to 3 sat? And thus, does that make this problem a exponential solution only kind of problem? And you can actually go in and archive, which is a computer science sort of like research database. I had my head TAs go in and like look at it once. We noticed that like there's probably at least like 25 NP complete problems being proven every month. So now there are thousands and thousands and thousands of problems that are all in disguise 3 sat. And I mean, these are problems like how protein strains might impact cancer, the human genome and how it relates to our genetic sort of composition and creation, password encryptions, all of the problems that we rely on to be so prohibitively complex that people can't just say run a password cracker and then like try all the permutations and get through stuff, right? Like we're just collecting this massive category of things upon this shared definition of 3 sat. And so now the plot thickens, if you will, because if we had a solution to 3 sat, the ever-growing list of problems that are proven NP complete, we have an ever-growing list of powers, an ever-growing list of answers to all of those problems. So there's literally thousands of NP complete problems. Some look wildly similar to things we've already chatted about. So for example, and I think I've mentioned this a few times, shortest path. So shortest path is, like we run Dijkstra's. You all implemented Dijkstra's, or if you haven't, hopefully you're doing that because it's due next Wednesday. Dijkstra's can run on your machine, right? It feels like we should just like flip an alligator mouth, right, and get like the longest path. But actually it turns out that's not the case. Finding the longest path through is actually an NP complete problem. If I give you the path, you can probably like trace it and be like, oh yeah, this is the longest path, right? But there is no p polynomial time way to find the longest path through a graph. So that is thus what we would consider an unsolvable problem. Click, click, click. There it goes. Other examples. So spanning tree, right? Like we can do spanning trees. Traveling salesman, a classic problem. Given a weighted graph, find a tour, a walk that visits every vertex and returns to its start. That is the shortest. Think about how useful traveling salesman would be, right? Like for shipping. Amazon, imagine how badly Amazon wishes there was a solution to traveling salesman. But as it turns out, there is not. There is not a p polynomial time way to find the shortest, like, full tour within a graph. So traveling salesman is an NP complete problem. Click, 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 click. I don't know what's happening. Yes, thank you. There we go. Like electrical companies, all that good stuff, right? So, okay, I tell you this because, again, I actually do think it is really helpful to be aware of what is considered efficient and what's not. And also, I don't want any of you to end up in one of those situations where you find yourself trying to solve what is an unsolvable problem in disguise. So if you find yourself working through something and you can only find a way to solve it that has to check all the permutations and has that recursive 2 to the n structure, right? Check if it's an NP complete problem before you waste too much more of your time. But that's not a very satisfying answer because like we still have to go like get in the truck and go do deliveries, right? So here's a few different ways that we can deal with an NP complete problem other than just giving up on it. So one, maybe in sort of like theoretical asymptotic analysis, it's coming out as NP complete, but maybe there's like a special case that we can find out faster. So maybe we don't need to have to solve the general problem, like in any given graph of any size, find a perfect tour, but rather can we find a smaller scoped answer? That's the special case solution. So instead of trying to solve the general problem, scope it and scope it and scope it until you get to a problem that's so much more limited that you can use a polynomial sign. Option two, maybe it's a special case we just don't understand yet. And in that case, what people usually do is they take their problem, and if they can't reduce it, so if they can reduce it down to 3 sat, that means it's an NP complete. A lot of times what people will do at that point then is see if you can start finding special cases in that problem that can reduce to 2 sat. So like, can we do something where we don't need all 3 of the Booleans for 3 sat? Can we find a special case where I really only have 2 Booleans that I need, 2 variables? Because I have a efficient solution to that. So when in doubt, see if we can apply that magical 2 sat solver. And then option 3, and this is the one that probably gets the most usage and could come up in your actual like industry lives, is what we would call an approximation algorithm. And an approximation algorithm is like, okay, maybe we can't find the exact answer, but like, can we get close? And so in this case, for example, in Traveling Salesman, instead of saying, given a weighted graph, find a tour or walk that visits every vertex of the shortest possible path, maybe we just go like, of a weight at most k. Meaning like maybe it's not the perfect absolute smallest, but maybe we sort of pick a threshold and we look for a value under that threshold. That actually does have a p polynomial time solution. And that is how Amazon calculates its routes. They're not looking for the absolute shortest path tour, but they set some type of boundary and then run an algorithm that's like, okay, can you find us a tour that runs in at least like 8 hours of driving or something like that? So yes, find minimum spanning tree, have the tour follow. There you go. Boom. That's actually a solution to the Traveling Salesman approximation. So it's not actually solving the Traveling Salesman, but it is a way to find a sort of reduced overall size minimum spanning tree tour. So, and this is, if not the most canonical industry thing, if you can't find an answer to the question they're really asking you, change the question, right? That's really what this is. Okay. So that's how to deal with those like impossible problems. But really, why are we talking about this? Why do we care that P and NP are not necessarily the same complexity class? I will tell you right off the bat, most computer scientists are pretty convinced that like just because you can verify something in polynomial time does not mean you can solve it in polynomial time. And in fact, we're so convinced of that, the foundations of how we've designed all computers and software rely on the fact that P and NP are not in the same complexity class. So we're so convinced of this, we've pretty much just decided we're all in on assuming that just because you can verify doesn't mean you can solve. So why do we care? Like I've been talking about, the Clay Mathematics will give you $1 million to anybody that can solve it. You'll definitely get a Turing Award. But that's probably more accurate. I mean, like literally, like I said, this will transform the entire world if you actually prove this. Because like, let's suppose that P and NP are the same complexity class. That would mean that a lot of things that we've built are built predicated on the idea that you can't just undo them with enough compute power. For example, encryption, right? You ever try to log into a website and it says you only have so many tries? That's specifically because they don't want you to bring a computer and just try permutations of passwords. Because right now, the only way to really break a password is to just try a bunch of permutations, right? Unless somebody's encryption algorithm gets leaked and then you can reverse engineer it. But right now, there's no more efficient way to crack a password in the generic sense than to just like try everything. But if we proved that P and NP are in the same complexity class, that means that there is an efficient time algorithm to reverse engineer every password and undo every bit of encryption that exists in this world. So you can imagine, yes, okay, we could decrypt all current internet communication. We could unlock every single password. No more secure online shopping or online banking. No more secure anything. Think about how different the world would be if there was an efficient solution to all of these NP and NP complete problems. And so, like, generally, what this means that P does not mean NP is it really means that there is actually ways to obscure information, that there is no clever secret trick to just undo encryption. And so that's why, like, we're all sort of predicated on this. There we go. Let's see. Yeah, okay, that's my last slide. So I always teach this problem, mostly because I think it does teach us something about how the world works. It also helps you understand a little bit of why we're obsessed with complexity classes. And also, I don't know, y'all, maybe somebody here someday will prove that P and NP are not in the same complexity class. And then when you get that shout out, yo, you better shout me out in your award acceptance speech, okay? That's all I want. Amazing. Thank you all so much for coming. We have 2 more lectures. On Wednesday, we're going to talk about memory, and we're going to move entirely away from theory and entirely in the direction of the actual physical communication of electrons within the computer. And then on Friday next week, the TAs are going to come, and we're going to do an AMA panel with TAs and myself. So please come next week. Have a wonderful long weekend. Don't come on Monday. No one will be here. Yeah? Thanks so much, everybody. Enjoy the sun.